Nearly 13.8 billion years ago, the universe began with the Big Bang. In its earliest moments, the cosmos was almost perfectly uniform, a vast ocean of hot plasma expanding in every direction. But it was not completely smooth. Tiny fluctuations in density, likely originating from quantum effects in the earliest moments of cosmic inflation, created slight differences in how matter was distributed across space. These variations were incredibly small, yet they would shape the entire structure of the universe. Over millions of years, gravity slowly amplified these tiny irregularities. Regions containing slightly more matter began to pull in additional material, growing denser and heavier. Gradually, these growing clumps of matter became the first seeds of cosmic structure. From this nearly uniform beginning, the universe began transforming into a complex network of galaxies, clusters, and immense cosmic filaments. Although galaxies appear to be made of stars, gas, and dust, these visible components account for only a small fraction of their total mass. The majority of a galaxy's mass is invisible. Astronomers call this mysterious substance dark matter. Dark matter does not emit light and interacts very weakly with ordinary matter, yet its gravitational influence is immense. It forms massive halos that surround galaxies and dominate their gravitational structure. These dark matter halos acted like gravitational scaffolding in the early universe. Normal matter, known as baryonic matter, fell into these halos under the pull of gravity. As gas accumulated within them, the conditions necessary for galaxy formation began to emerge. This process is described by the lambda cold dark matter model, the leading cosmological framework explaining how structures formed after the Big Bang. According to this model, galaxies grow through gravitational clustering and repeated mergers with other systems. Within the invisible architecture of dark matter, the visible universe began to take shape. When astronomers observe galaxies across the universe, they discover that galaxies come in many different forms. One of the earliest classification systems was developed by Edwin Hubble. Known as the Hubble tuning fork diagram, it organizes galaxies into several main categories. Some galaxies are spirals, thin rotating disks filled with stars, gas, and elegant spiral arms. Others are elliptical galaxies, massive systems where stars move in random directions rather than orderly rotation. There are also irregular galaxies, which lack clear structure. Despite this diversity, most galaxies fall into two major populations. The first group consists of blue galaxies, which are rich in gas and actively forming new stars. These galaxies are typically spirals. The second group contains red galaxies, which have little gas remaining and have largely stopped producing new stars. These galaxies are usually elliptical. Another remarkable feature found in many galaxies is the presence of supermassive black holes at their centers. These objects can contain millions or even billions times the mass of the Sun, and their mass is closely connected to the size of the galaxy surrounding them. Understanding how these different galaxy types emerged is a central question in the study of galaxy formation. The earliest galaxies likely formed as rotating disks. In the young universe, enormous clouds of gas began collapsing under gravity within dark matter halos. As the gas contracted, it cooled and moved toward the center of these halos. But the collapsing material was not perfectly still. Small gravitational interactions between neighboring matter clumps gave the gas angular momentum, a slow rotational motion. As the cloud shrank, this rotation increased, much like a spinning figure skater pulling in their arms. Eventually, the collapsing gas flattened into a rotating disk. Within this disk, regions of gas became unstable and fragmented into smaller clouds. These dense pockets of matter collapsed further, igniting nuclear fusion and forming the first generations of stars. Over time, the organized rotation of the disk created the spiral structures that characterize many galaxies today. Yet, the exact details of how these disks form and how their size and rotation speed are regulated remain active areas of research. Early astronomers proposed different explanations for how galaxies first assembled. One of the earliest models was known as the top-down theory. In this scenario, enormous gas clouds collapsed directly to form galaxies. The cloud would contract, flatten into a disk, and then fragment into stars. However, later observations suggested a different process. Modern cosmology favors the bottom-up model, also known as hierarchical formation. In this view, the universe first produced many small structures, objects comparable in mass to globular star clusters. Over time, gravity caused these small clumps to merge together. Repeated mergers gradually built larger and larger systems, eventually forming full galaxies. These galaxies themselves then gathered into groups and clusters. This hierarchical process explains why the universe contains many more small galaxies than large ones, matching what astronomers observe. Galaxies are not isolated islands drifting forever through space. Gravity continually pulls them toward one another. When galaxies pass close together, tidal forces distort their shapes, stretching stars and gas into enormous streams. In many cases, the galaxies eventually collide and merge. These mergers can dramatically transform the structure of galaxies. When two spiral galaxies of similar size collide, their orderly rotating disks are often destroyed. The stars are thrown into new random orbits, and the merged system becomes an elliptical galaxy. The collision also compresses enormous clouds of gas, triggering intense bursts of star formation. Entire regions of space ignite with the birth of thousands of new stars. Such mergers are among the most violent events in galactic evolution. Even our own galaxy is part of this story. The Milky Way and the nearby Andromeda Galaxy are gravitationally bound and slowly moving toward one another. In less than 5 billion years, the two galaxies are expected to collide. The result may be a single giant elliptical galaxy. Not all galaxies continue forming stars forever. Astronomers observe that many galaxies eventually stop producing new stars and transition from blue, active systems into red, passive ones. This process is known as galaxy quenching. Stars form from cold gas. If a galaxy loses its supply of cold gas, star formation quickly shuts down. Several mechanisms may cause this transformation. In some cases, a galaxy entering a dense cluster environment may lose access to fresh gas. Gravitational interactions with neighboring galaxies can prevent additional material from falling into the system, a process known as strangulation. In other galaxies, powerful activity near the central supermassive black hole may drive enormous jets of energy into surrounding gas. These outflows can heat or expel gas entirely, preventing it from collapsing into new stars. Through these processes, vibrant star-forming galaxies slowly fade into quiet stellar systems. Because galaxy formation unfolds over billions of years, astronomers cannot observe the entire process directly. Instead, they turn to powerful computer simulations. These simulations combine the physics of gravity, fluid dynamics, star formation, and black hole activity to recreate the evolution of galaxies across cosmic time. Scientists model how gas cools, how stars form inside dense clouds, and how exploding supernovae inject energy back into their surroundings. They also simulate the growth of supermassive black holes, the influence of magnetic fields, and even the effects of cosmic rays moving through interstellar gas. By comparing these simulations with real observations, astronomers refine their understanding of how galaxies evolve. Each generation of simulations brings us closer to reconstructing the true history of the universe. Today, billions of galaxies fill the observable universe. They gather into enormous clusters and trace vast filaments stretching across cosmic space. Yet galaxies are not static objects. They continue to merge, evolve, and transform over billions of years. Stars are born, galaxies collide, black holes grow, and cosmic structures expand. From tiny fluctuations in the earliest universe emerged the vast galactic systems that now illuminate the cosmos. And among those galaxies is one spiral system that we call home. But every galaxy has its own origin story. And in the next episode, we will explore the formation of our own cosmic home, the birth and evolution of the Milky Way galaxy.